Hypothalamus artificial intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called Smart Grids, Buildings Optimization. Lecture prepared by Engineer Jesus Velasquez Bermudez, Ph.D. Hypothalamus Artificial Intelligence, HAI, and the Research Center for Advanced Decision Technologies, RCADT, a private graduate academic center that uses artificial intelligence to complement advanced professional training, are pleased to invite you to watch the podcast of the course, Smart Grids Optimization. In 2014, IBM estimated that companies in the energy and utilities sector, which used big data and analytics, reported 23 times higher productivity than those that did not. Smart Parking. Smart Parking, Network, Infrastructure, and Urban Service. In urban areas, parking coordinates land use and transportation, and is one of the most important assets, as it generates revenue for the city. When the urban population grows, there are more cars circulating and they tend to stay in traffic. This generates 30% of traffic jams because they are going to park and expect to get cheap or free parking on the street. Some French municipal statistics have shown that the hours wasted searching for parking are at least 400 hours a day in the city's business district. Those hours into fuel consumption, CO2 emissions and the economic effect, parking is very expensive, both from a personal, public and environmental point of view. In smart parking, drivers get real-time availability information from their smartphone and can adjust the travel schedule. Many cities have launched their smart parking projects, but still very few drivers can benefit, because the technology needs to be improved from different perspectives: the robustness of the sensors, the stability and timeliness of the sensor networks, the quality and agility of the urban service, and the user-centric consideration. In addition, smart parking must deploy many sensors and overcome current sensor management problems. It can become a leading paradigm of smart cities. HAL is a multidisciplinary open-access archive for the deposit and dissemination of scientific research documents, whether published or not. Taxonomy of smart parking solutions. Parking has been a problem for all drivers and has become a field of industrial research and development. Smart parking seems to be a viable solution for our cities, integrating knowledge from different disciplines. Smart parking is the first solution to alleviate growing traffic congestion. Many cities have begun to implement the service from different perspectives. An essential smart parking service includes two flows: information and traffic. The flow of traffic occurs on the way to look for parking. Typically, drivers receive information about availability, head to desired areas, and then park. According to the city's communication technology, drivers could only obtain partial or outdated information and would have to repeat the search. When there are many drivers looking for parking, competition arises that generates accumulated parking conflicts. The behavior varies depending on the information drivers have, how long they have been driving on the street. Once a vehicle enters to, or leaves from, parking lot, information about availability changes and must be communicated to drivers looking for a space. To obtain the occupancy status, fixed or mobile sensors are installed on the street of the car park to detect traffic incidents. The sensors form a network and send the information to the data storage devices. Drivers can get the latest information using variable message signals, VMS, or their portable smart devices, which exchange messages with roads infrastructure, RSI, or base transceiver stations, BTS. Although there are many deployment projects and applications, in 2015 very few drivers can still really benefit from smart parking. Spark, San Francisco, and LA Express Park, Los Angeles, are two most famous successful stories while talking about smart parking. But if we try to deploy the same system in another city, it is always essential to do a preliminary test, choose the most appropriate technology and adjust the system according to the layout of the streets and the habits of the inhabitants. For example, Nice is the first French city where a smart parking project was launched in 2012, named Nice Park. The main characteristics of the project are: 10,000 sensors are planned to be installed in 13 different parking areas. A smartphone app has been developed that allows drivers to check parking availability information from their phones. Parking sensors are connected to nearby multi-service parking meters. For those who don't have a smartphone, they can pay for their parking spaces, get up-to-date availability in the city, and get information about tourism or public transport simply by using multi-service parking meters. The cost of the deployment is estimated at between 13 and 15 million euros. The literature on smart parking solutions is highly diversified. Not only does it balance land use and traffic, but it also connects inhabitants with urban resources. The figure proposed categories of smart city solutions and the spectrum of disciplines related to topics. Parking system deployment is the main work of service providers. The user interface and information processing shall be adapted to the service type. Here, we divided the parking system deployment into three parts: software system, large-scale deployment, and data prediction. Parking is a city-level issue. The three types of urban detection are mobile, fixed site through short-range communication, and fixed site by long-distance communication. Parking vacancy prediction. According to the prediction, the smart parking service may offer the possibility of getting a parking space for drivers. The most popular prediction theory carries out a Poisson arrival process and then predicates the capacity of the system using the Markov chain. It is assumed that the demand for parking is directly proportional to the vehicle population. Many different prediction models can be used to forecast parking demands. Some examples are: we introduced 5 forecasting methods. Parking generation rate, vehicle population, land use analysis and impact on traffic, travel attraction based on origin-destination data, and multivariate regression based on historical materials. Pulola and collaborators modeled the availability of a car park using a Poisson process and then proposed an algorithm to give the probability of availability of each parking space when the customer arrives. Klappenecker and collaborators assume that the arrival of the vehicle follows a Poisson distribution and modeled the parking using Markov chains and continuous time. Then, with the expected occupancy status, each parking lot provides cruise vehicles with availability information through vehicle networks. Parking service dissemination can be divided into 3 parts: information dissemination, parking competition, and driver behavior. Information dissemination. All the existing large-scale deployment adopts a centralized method to provide parking information via cellular link or Wi-Fi. The flow of information supported by road infrastructures and vehicle networks is also common. The City-Based Parking Route System, CBPRS, proposed a centralized parking system that connects smart streetlights and parking sensors using powerline communication. Some of the methods used are: an optimization methodology to guide drivers from their current locations to parking spaces. The results show that the optimization methodology reduces traffic congestion and increases city flow. Modeling based on the impact of the parking guidance system that varies the saturation rate in the market and the demand. The results show that it can significantly alleviate the difficulty of parking in urban areas. Using parking sensors that periodically send available information to vehicles so that they can find spaces in nearby places. Parking competition. Dynamic pricing is the most efficient way to regulate parking occupancy status and traffic congestion. Unlike a fixed dynamic pricing policy that changes the price according to occupancy in a review period, there are alternative methods based on a dynamic pricing policy with a Markov chain model, which can predict the demand for parking spaces, and adjust the price before it becomes congested, or is used as underused. Some bibliography. Dulames et al. Use smart parking reservation policies using maximum intervals and dynamic pricing. Pricing is often combined with a multi-agent system, which makes it possible to describe the behaviors of different individuals and interactions between them. Cho et al. Model price negotiation with a multi-agent system. Each car park manager announces the spaces and waits for offers from potential users. Thus, the price of parking will change dynamically according to the intensity of the competition. Delarco et al. Propose to match the demand and supply of parking under dynamic pricing using a multi-agent system. The cost of parking perceived by drivers is described with a fuzzy set to show the imperfect knowledge of both the parking and the state of the system. Di Napoli et al. Propose a software agent negotiation mechanism, which establishes an agreement between drivers and the parking manager considering the preferences of the drivers, for example, location and cost. Drivers' parking behavior. Parking behavior is an important criterion for an intelligent parking system, where each driver has his or her own preferences. The behavior focuses on the parking system. Guo et al. Formulated numerical models for passing, parking and unparking vehicles and ran them in Monte Carlo simulation. As parking probabilities and vehicle arrival rates change, traffic and system capacity are also affected. ParkAgent is an explicit agent-based spatial model for parking in the city. It simulates the behavior of each driver to generate distributions of key values such as search time, walking distance, and parking costs between different groups of drivers. It also shows that the additional supply of parking linearly affects the occurrence of extreme values but has only a weak impact on the average time spent searching for a parking space or on the average walking distance between the place and the destination. The results show an ethnographic study in whether drivers are aware of dynamic pricing policy and mobile telephony. Urban sensing using a wireless sensor network. Population growth generates economic growth and denser urban mobility. Thanks to smartphones, drivers can get various information simply through mobile apps. Thus, the availability and quality of urban information become one of the most important criteria for smart cities. User-generated information is the first proposal and enriches the sources of information from different perspectives and facilitates the sharing of interesting information according to the sudden or periodic urban mobility of users. However, the content posted may be outdated, or false, due to a lack of participants or malicious users, as well as being limited to human observation. Networked wireless sensors help to obtain more types of information and ensure accurate measurements by sending regularly updated information or on demand. That is, a network packet consisting of certain information must be treated with its priority to respect an acceptable information delay. The increase in mobility motivates new urban services to be carried out by sensors connected to the network. Traffic congestion is one of the main problems in the metropolis, and a large percentage of traffic jams are due to vehicles looking for parking. Urban drivers require an intelligent on-street parking system assisted by networked sensors to shorten the search time and distance to destinations. These networked parking sensor devices detect the availability of parking spaces and form a wireless sensor network, WSN. Such a so-called parking sensor network, PSN, inherits its energy and delay constraints. To optimize network parameters for best performance, the network traffic is significant. Two mainstream traffic models are request, event and time-driven. Request-driven models are irrelevant for parking sensor networks since continuous recording is required for municipalities. Time-driven are often used in testing the performance of network protocols because of their low dependence on the environment. Event-driven application is tricky due to its variety on different types of observed events. PSN has the next characteristics. Parking sensors are stationary, in-ground and scattered with a minimum adjacent distance. The network topology is linear and limited by the urban street layout. The sensing areas of the parking sensors do not intersect to avoid multiple detection. Packet generation rate depends on the vehicle's arrival and departure, and the availability of parking places should be delivered as a real-time service. Based on these, we see the importance of device lifetime considering their maintenance and latency while providing real-time service to urban citizens. The topology of urban sensors is strongly related to the sensor type and city map. In PSN, sensors are installed on parking places. Since the implementation of the Spark project, the deployment of the network is quite consistent. All wireless parking sensors are buried and have limited communication with each other due to soil swirls and vehicular obstacles. Thus, sensors regarded as reduced function device, RFD, can only communicate with routers or gateways which are full function device, FFD, and generally mounted on the streetlights or traffic lamps in crossroads. Packets generated on parking sensors have to travel from the closest routers hop by hop until they reach the gateway. The typical topology of parking sensor networks can be categorized into three groups. Crossroad. Most routers or gateways are installed crossroads to reach their maximum coverage, i.e., Each router or gateway can manage more sensors while installing in crossroads. Line: for some long road segments, routers might be needed to guarantee sensors connectivity, and mesh: when enlarging the deployment scale, the network will be constituted of many small crossroad and line-type topologies. Spark project in San Francisco. In 2015, based on this, large-scale roadside parking sensor network has been implemented in many cities, such as Spark in San Francisco, LA Express Park in Los Angeles, Fast Park in Barcelona, Connected Boulevard in Nice, and so forth. The most famous project is Spark, that covers 30% of street parking. Sensors and meters can both communicate wirelessly. One repeater at almost each intersection completes the wireless mesh networks. 85% events can be received in the central server within 60 seconds, taking advantage of vehicle mobility to collect information along the route with fewer sensors. The main goal of Spark is to guarantee a 75% occupancy rate in any parking area by a dynamic pricing policy. Drivers, who park their cars on on-street parking places, can easily extend their parking time and pay from internet. The payment information will be updated and showed on parking meters. Besides, parking meters have an internal clock and can turn off themselves during parking time to reduce energy consumption. Some big companies work on the service integration to enrich the functionalities of parking meters and their interaction with drivers, for example Xerox PARK. Information detection relies on sensors to collect parking availability in real time. Two types of sensors are used. Fixed sensor that adds detection capability in parking spaces. When the occupancy status changes, the sensor detects the presence or absence of vehicles and updates the information. Mobile sensor that can detect the occupancy status when you pass by the car park, so the information can be updated for a long time. Smart Parking City projects until 2015. The figure shows the sensor occupancy status timeline on the left, the sensor state transition diagram on the right. In PSNs, the main observed event are vehicles' arrivals and departures. For any parking sensor, each vehicle arrival accompanies exact by one departure prior to next arrival. To model it, we first look at the event occurrence sequence on one parking sensor. Each parking sensor is precise enough and provides merely two states, occupied and vacant. The inter-arrival time, CDF, has a tail that varies regularly such that the distribution functions are Weibull-like. Routing protocol. In a multi-hop mesh network, the impact of the routing protocol is important on performance. To initiate routing discovery, the gateway sends a hello message to the network with a value of 0, sequence number, gateway address, and the sender's last address. Each device that receives this message increases the value by 1 and then stores it in its own cost table. If the lifespan of this message has not yet expired, it will be forwarded back to the internet. Each device can receive multiple messages, however, it will choose to send its packets the one with the smallest value. Gradient routing ensures that routes are assigned in only one direction from the gateway and retains half of the control messages. The figure shows a multi-hop parking sensor network that depicts the value of each device in a packet flow using gradient routing. Fixed sensor networks pick up their packets on gateways. Gradient is currently the most energy-efficient routing protocol. Event-driven traffic. Inter-arrival time, CDF, stands for the interval of two consecutive vehicle arrivals to different parking spaces in the area. Each parking sensor sends a packet when its detection status changes. CFS is limited to the vehicle's inter-arrival time, and it will also be loaded with the parameters of shape and scale. The figure shows the parking map with 120 parking sensors. Each parking sensor is precise enough and provides merely two states, occupied and vacant. The figure shows the CDF and the survivability function of the inter-arrival times of vehicles and packages of a parking sensor on the ground. Each sensor sends a packet when its status changes. CFS is limited to the vehicle's inter-arrival time, and is loaded with shape and scale parameters. A group of sensors is analyzed and the arrival time for a parking area is evaluated. The CDF corresponds to the interval of two consecutive arrivals to different parking spaces in this area. The figure shows the survival function of vehicle and arrival times of 2, 5, 10 and 24 in-ground parking sensors. The figure shows the CDF and survival function of vehicle and packet and arrival times of 24 in-ground parking sensors. The figure shows the periodic and event-driven mixed application with different combinations. The figure shows the generated packets by event-driven traffic model while all sensors have the same scale parameters. In the figure, the property of non-uniform is most evident when the shape parameter is less than 1. This is because the infinite mean and infinite variance generate greater variation between the parking lot sensors. Figure shows that the packet generation rate is strongly decided by the sum of the parking time and the available time. The figure shows the difference in traffic between sensor nodes, while all sensors have the same average inter-arrival time, but different shape parameters, 0.5 and 1. The figure shows the timeline of network traffic when having the same scale parameter but different shape, parameters 0.5 and 1. The network load managing 24 parking sensors. It's clearly that when the shape parameter is 0.5, the network traffic explosion is more significant and cannot be considered as an exponential distribution. Periodic time-driven traffic. Periodic application is only affected by the traffic interval rather than the frequency of occurrence of the event. The number of packets generated is inversely proportional to the traffic interval. By using a periodic traffic model, the amount of traffic is not affected by sensory input. Simply send a packet with the current state timestamped when the time runs out. A third case is the hybrid periodic and event-driven traffic. Assuming that the sensory information is small enough to merge with the packet along with the energy state information, a time parameter is defined as the threshold for deciding when the information is to be sent. Media Access Control, MAC, protocols have been the subject of much controversy in urban sensor networks. 4 different types of MAC protocols are containment-based, calendar-based, and hybrids of both, respectively. These protocols are all service cycle, scheduled, and run in a time-synchronized environment. To minimize downtime in each data slot, each transmitter sends a very small message to reserve the medium before starting data transmission. If the reservation fails, the transmitter will put the packet back in its queue, turn off the radio, and wait for the next time slot. Rather than wasting energy on a vain transmission, sensor nodes prefer to assess receiver availability through these very small beacons. Considering that WSN is usually limited in bandwidth, the only average resource is time splits in a single channel scenario. The figure shows the radio behavior of sensor device, in the case of periodic time-driven traffic. To implement this, 4 different radio states emerge to meet the requirement. Transmission, radio_TX, reception, radio_RX, carrier sensing, radio_CS, and radio off, radio_off. The figure explains the differences between CSMA, TDMA, funneling MAC and IQs. MAC protocol deal with the data transmission in the contention access period, CAP. For a better comparison in CAP, these 4 MAC protocols apply the same amount of time slots, and the hybrid versions will adjust the percentage of TDMA or CSMA slots to combine the advantages of TDMA and CSMA in one protocol. All devices run CSMA by default. Funneling MAC is a hybrid version of TDMA and CSMA. The devices, which are n-hop away from the gateway, will change to TDMA and then ask for a time slot to the gateway. IQ sets a 1-byte queue indicator on the MAC header, so that the gateway will be informed of additional demands from data packets and respond with some additional time intervals from variable TDMA slots, called TMA. The topologies are shown in the figure, and show different numbers of sensors. The density of nodes increases by adding one more line, or one more side of the parking side on the sidewalk. The simulations were carried out with the WSNet simulator. The first takes a small cell at a junction with different network density for scenario 1. The figure shows 3 different topologies for the simulations, referring to the 3 regions with traffic parameters for scenario 2. To clarify the influence of 4 different MAC protocols, we chose a set of parameters. R1, crossroad, 1 gateway and 24 parking sensors. R2, line, 1 gateway, 1 router and 24 parking sensors, and R3, mesh, 1 gateway, 5 router and 60 parking sensors. The figure shows the Map 1, Lyon on-street parking map between Place Bilcourt and Place Carnot. Map 1 has a grid-like parking distribution. The red dots indicate the selected intersections to install WMIs, a schedule-based media access control protocol, and an event-driven application, are the most suitable for the scenarios in Map 1 and 2. The figure shows the Map 2, Lyon on-street parking map between Place Turreau and Place Bilcourt. Map 2 is less regular because of pedestrian areas. The total parking area length in both maps is approximately the same. However, Map 2 has 27% more crossroads than Map 1. It is important to provide engineering insights to streamline the WSN construction of urban smart parking application. The BA method is the utmost important key point of determining energy consumption and information delay when traffic and node densities are known a priori. We applied 2 fundamental types of BA to our simulations instead of choosing particular protocols. In this way, we can see clearly that how the traffic intensity and node density affect the network performance, and the results could serve as guidelines for urban sensor network designers. The figure shows the best configuration versus vehicle activity and network density. The figures show the average hop count, information delay, versus the amount of deployed IGW, cost. Map 1, at left, and Map 2, at right. The figure shows per node energy consumption, while varying N and traffic parameters under schedule-based B. A. Periodic, at left, and event-driven, at right. The event-driven has low energy consumption. The figure shows per node energy consumption, while varying N and traffic parameters under contention-based BA. Periodic, at left, and event-driven, at right. The figure shows information delay of event-driven application while varying traffic parameters and node number under schedule-based BA. The figure shows information delay of event-driven application while varying traffic parameters and node number under contention-based BA. The figures show the survivability function of packet interarrival time on the side of the gateway. 3 cases are considered: crossroad, line, and mesh. 4 information delays are analyzed in each case: CSMA, TDMA, funneling, and I/Q. The figures are a mixture of types of crossings and lines. As the size of the network increases, so does the probability of packet arrival. It is evident that different MAC protocols make a slight difference. However, the interarrival time is still roughly an exponential distribution, therefore, it may be possible to apply a Markovian model. The figures show the information delay of a changed parking occupancy status. CDF is the information distribution, giving the probability of getting a better response with respect to the distance between messages' current location and the destination. For example, the mesh case shows that IQMAC has a good performance as CSMA, but the slot allocation still requires at least 1 packet transmission in the CSMA time slots of CAP. TDMA has a very long information delay because of its longer duty cycle and the construction of multi-hop scheduling. The schedule can be optimized when the network topology is known. The figures show the lifetime of parking sensors 0.1s and battery capacity 6.3Ah. For example, the case of line shows the power consumption of the linear topology R2. It is evident that all MAC protocols have a higher energy depletion deviation, except for TDMA. This is because it is the only containment-free, schedule-based MAC protocol in our scenarios, and half of the nodes must work in multi-hop networking, which causes a hidden terminal problem. Funneling MAC performs very poorly in linear topology due to the unbalanced allocation of TDMA slots for the router. To test the model, different kinds of scenarios with the corresponding parameters was constructed. The table shows the simulation parameters for vehicular network and mobile network. The figures show the per day consumed energy and transport power output of event-driven. At left, under contention-based, and at right, under schedule-based. Deployment of urban infrastructure. To analyze the above problem, The following methodology defines four objectives: energy, connectivity, cost, and latency of the multi-hop mesh network. From these constraints, we can also derive some parameters relevant to the sensor's lifetime and the delay in detecting information. Two graphs are an on-street parking network and a set of wireless links to indicate the relationship between two given intersections, which have the same length of on-street parking area, but with a completely different street layout. Finally, the adjacent matrices are taken as the data inputs of the constraints, and an attempt is made to optimize them. Gateway and router deployment. To analyze the above problem, the following methodology defines four objectives: energy, connectivity, cost, and latency of the multi-hop mesh network. From these constraints, we can also derive some parameters relevant to the sensor's lifetime and the delay in detecting information. Two graphs are an on-street parking network and a set of wireless links to indicate the relationship between two given intersections, which have the same length of on-street parking area, but with a completely different street layout. Multi-hop modeling. Optimal deployment of urban roadside infrastructure to reveal the relationship between the cost and the network performance. The multi-hop networks is designed according to multiple objectives, for example, network latency, energy consumption, deployment cost and sensor coverage. Multi-hop model. Now, the problem of deploying a smart mesh network of multi-hop parking within the city's infrastructure and solving it with a multi-objective optimization approach is considered. The following ideas should be considered about the design of the parking sensor network. First, the total sensor energy is determined by the number of intersections and is inversely proportional to the number of active WMIs. Second, the delay in the detection information is related to the average degree of complexity of the street parking graph. Therefore, the complexity of the layout of the city's streets is an important factor when it comes to building urban infrastructures. Third, the deployment of the IGW can be considered a clustering problem in the geographical position of parking sensors. Once the WMI selection is made, the cluster number will be the minimum number of IGWs deployed. Fourth, we show the trade-offs between sensor lifetime, lag in information, and cost of urban infrastructure to be provided as a guide and considered when integrating with pre-existing infrastructure. An extended content-based publish-subscribe service. Thanks to the rapid growth of machine-to-machine, M2M, communications technology, cities are ready to deploy urban services. Smart parking has been one of the first services implemented in smart cities, and smart parking applications have proliferated. As early as 2015, they offered a graphical interface for drivers to choose their preferred parking spaces. However, parking information changes dynamically and it is always forbidden to use a smartphone while behind the wheel. For this reason, the publish-subscribe service has become the most favorable event messaging paradigm for urban services. It is designed for users interested in various spatial temporal information, especially in urban areas. Users must describe their interests as information subscribers through certain APIs, such as subscribe, subscribe_update, and unsubscribe. The source of information is the publisher who disseminates the data. It must connect using publish, without knowing who its subscribers are. To get the information to the right subscribers, intermediate nodes in the network must read the content of the message and select the data of interest. If there is a specific server to handle publish-subscribe messages, we call it a broker, which maintains a list of subscriptions and a table of publications, and then makes notifications when there is a new subscription or a new or updated publication. To notify all subscribers, a multicast or multi-geocast route of the underlying network is required instead of a transmission. This event messaging paradigm is an application-level network, as the flow of data is driven by users' interests and geolocations. As a result, the network path between the publisher and the subscriber can be long depending on the behavior of the brokers. Smart municipal parking services often adopt parking sensors as a source of information. If there is any change, the sensors publish their occupancy status to the nearest gateway, such as the road infrastructure, RSI, or the info station. Parking detection sensors are usually deployed on metropolitan networks and are restricted to the urban layout, as are the drivers and the corresponding RSIs. The parking information available is collected by the RSIs from sensors on the street and then appears on the driver's devices, such as in smart applications on smartphones or peer-to-peer network infrastructure. If RSIs and vehicles communicate over a mobile network, RSIs or with a central server can be the intermediary. If cruise vehicles obtain information from opportunistic vehicle networks, vehicle-to-infrastructure, V2I, and vehicle-to-vehicle, V2V, vehicles and RSIs can be intermediaries and form a structured overlay. In this way, each vehicle has a public buffer to store shared information and other private ones for personal use. Service-Centric Continuous Announcement Messaging Paradigm, SCAMP. The author, Trista Lynn, proposes the Service-Centric Continuous Announcement Messaging Paradigm, SCAMP, to have urban information in a reflexive way, considering the optimums already achieved from existing centralized solutions. SCAMP is deployed in totally opportunistic vehicular networks, so that information will travel between cars, V2V, and RSIs, V2I. To solve the parking conflict problem, SCAMP adopts a continuous update service to disseminate parking information in real time, such as an extended publish-subscribe messaging paradigm, which allows specify and subscribe to the information of interest and then receive a push if there is any update. Sets of publications and subscriptions must be kept distributed and dynamically. All vehicles and RSIs can perform a comparison of data of interest to target new or updated posts to the right subscribers and vice versa. The increase in vehicles causes a packet collision disaster and reduces network performance, resulting in drivers not being able to get the information and resulting in a drop in occupancy rate. However, with SCAMP the user's query does not always have to reach the geocast region to get answers. SCAMP maintains the publish and subscribe tables wherever subscribers are. A good publication and proper subscription table result in a match of interests and data, without losing the performance of the service due to useless messages. With respect to geocast, SCAMP has a lower occupancy rate, because of its lower retransmission of packets to disseminate the information to controllers further away. Illustration of SCAMP. The figure shows an illustration of three-layered system architecture. Content layer contains two kinds of information, users' interests and parking data. Users' interests stand for subscriptions, in green, and sensed parking data are the publications, in blue. In logical layer, drivers know that the parking information is around their destination. Infrastructure layer shows the physical network in the real world. The data travel between vehicles and RSIs according to users' interests. The figures show the transmitted packets in an area of 9 square kilometers. At left via geocast, and at right via SCAMP. The difference in favor of SCAMP is an order of magnitude on the logarithmic scale. The commands are differentiated by the colors of the stripes. #unsub, #sub, #subupdate, #pub, and #tx. The infrastructure of a smart parking system it is composed of. Citywide wireless mesh infrastructure, WMI, comprising mesh routers, MR, and Internet gateways, IGW. The deployment of WMI networks at a citywide level with reasonable costs is the primary concern. The figures show a smart parking information flow, which includes sensors, MISs, and IGWs in metropolitan areas and provide real-time information to users. In the deployed sensors are generally scattered with a minimum adjacent distance of 2 to 5 meters to avoid multiple detections. The figure shows the deployment of Spark in Civic Center Zone. We see that R, the repeater, and IGW, the gateway, are mostly installed at crossroads in the real-life deployment, because most traffic panels are installed at crossroads with electrical cable. Some sensors might be too far from R, or IGW, thus multi-space parking meters are often used as a network relay. There are three main characteristics of the deployment of smart parking sensor network: energy, connectivity and timeliness. The table shows the parameters used in the multi-hop model. Multi-hop modeling represents the city's graph by the set of street intersections and the set of road segments between them. A citywide wireless mesh, WMI, comprising mesh routers, MR, and Internet gateways, IGW. The model defined the graph of a city by the set V of street intersections and the set E of road segments. Then, C, equal to the union of V and E, represents city graph. Two binary variables to express the status of each crossroad. Xi will be 1 if a WMI is installed in VI, 0 otherwise, and Yi will be 1 if a IGW is installed in VI, 0 otherwise. The deployment of WMI networks at a citywide level with reasonable costs is the primary concern. Due to the limitation of the soil medium and battery energy, the underground sensors communicate directly with roadside overground misses, and IGWs form wireless parking sensor networks in metropolitan areas and provide real-time information to users. If a citywide wireless mesh infrastructure, WMI, is installed in a segment, it can manage part of the sensors deployed on the adjacent road section. The sum of the partial segments managed by both intersections must be greater than the length of the road section. The density of parking sensors varies depending on the type of parking. For example, in a common parking space, the average distance between adjacent sensors is 5 meters, so the sensor density is 0.2. The maximum sensor numbers managed in each WMI is limited by the bandwidth allocation method. For example, a contention-based MAC protocol cannot serve more than 70 sensor nodes simultaneously when traffic intensity is high. A multi-hop wireless network of urban sensors is defined based on binary variables to express the relationship between intersections in the equations 4 to 12 to 4 to 14. For a node, its parent is the node that has direct communication and forwards its packets to the Internet. Its predecessor is the node that is responsible for forwarding its packets to the Internet, with IGW being its Internet portal. Each sensor can forward a packet to its available neighbor with the lowest height, shortest network distance. We define the multi-hop constraints based on the gradient-based routing protocol. Once the intersections to install the WMI have been decided, we will choose some to install IGWs and keep the remains for the misses. It is about solving a problem with multiple objectives. The number of WMI signifies network connectivity and indicates the lifetime of the sensor, and the number of IGWs takes care of load balancing. The average jump distance from the managed sensors to the nearest IGW is the information delay. Two optimization methods are considered. First, deterministic optimization assumes a blank area without any pre-existing WMIs. Second, stochastic optimization considers a set of pre-existing WMIs, and calculates how many additional WMIs we shall expect to install. A pre-scheduled transmission time for all sensors and misses are the focus on the relationship of the multi-hop networks. Two different street layouts was tested. The figure shows the total power consumption over the lifetime of the sensor versus the cost of the number of WMI deployed. The figure shows an example of a multi-hop network with an example of 4 WMIs. Node 3 is the Internet portal for all the others. Node 2 and 4 connect directly to Node 3. Node 1 connect to Node 3 via Node 2. Then, Node 2 is the parent of Node 1, Node 3 is the parent of Node 2 and 4, Node 2 and 3 are both the ancestors of Node 1 and Node 3 is the ancestor of Node 4. The table shows the values of the parameters Aij, Bij and Gi, when they are equal to 1. Hi signifies the hop count from the sensors managed by Mr. I to its IGW. Network capacity can be expressed according to the network distance of each Mr. The collected packets will be retransmitted Hi times, which generate more traffic on each ancestor. Thus, the traffic capacity will be restricted by the maximum capacity. The figure shows that the publisher and subscriber endpoints are performed at the application layer. However, the publish-subscribe service relies primarily on the logic layer, which provides the system with intelligence to handle events and ensure message exchange between the content and infrastructure layers. When publishers or subscribers send messages, which contain posts or subscriptions to the network, the logic layer must match them and then route the messages to the correct destinations. This means that a broker is deployed in the middle nodes to maintain sets of posts and subscriptions, and to execute interest data matching. The intermediate nodes decide how to process messages based on matching results, and some added information. Once subscribers receive the information, they can change their minds about what affects the geographic spread of the information. The image shows an example of driver subscription, left, and RSI's publication, right. The figure shows the illustration of a on-street parking segment with 2 gaps. The on-street parking zones in France are mostly non-demarcated. To collect the information from non-demarcated zone, we first assume that sensing technology is good enough to provide multiple detection with the length of available parking spaces. For each road segment with on-street parking, the available parking information is the number of gaps between two adjacent parked vehicles and their corresponding lengths. Figure A shows examples of matching results. Figure B shows the spatial partitions of a query area to evaluate whether the match result is good. If the matching area, in blue, is almost equal to the query area, the match is good and the matchmaker does not redirect this query. Otherwise, the matchmaker will check the spatial distribution by indicating the percentage of the matching parts in the different partitions. The table shows the set to decide if a message shall be forwarded, FW, responded, RE, modified to a new query, NQR, or responded according to the new query, NRE. The figure shows the mobility model. Since the network traffic correlates closely with drivers' behaviors, we define three different driver states. Driving state means that a driver has set a destination and steers to it. When a driver switches to this state, he will send an inquiry describing his parking subscription to get the parking information around his destination. Drivers can also update their subscription update while moving around the city. Once the driver finds a parking place, he will switch to the parking state, send a message to terminate his subscription, and park for a while. When the driver finishes parking and starts to be active again, he changes to the roaming state. The relationship between the parameters E and top is shown in the two figures. Their definition is E, generated packets, and top, urban areas of different sizes. The number of vehicles is half of the available parking spaces and 9 grids. The impact of top and E is evident. Both show that the larger they generate, the more subscription-based streams, especially considering a larger urban area. The figures show the ratio of transmissions to subscriptions, in an area of 1.44 square kilometers, on the left, and 9 square kilometers, on the right. The figures show the parking search time, in an area of 1.44 square kilometers, on the left, and 9 square kilometers, on the right. The figures show parking distance, in an area of 1.44 square kilometers, on the left, and 9 square kilometers, on the right. The figures show distance from parking to destination in an area of 9 square kilometers. At left via geocast, and at right via scamp. The difference in favor of scamp is greater when there is less congestion. The figures show time to find a parking place in an area of 9 square kilometers. At left via geocast, and at right via scamp. The difference in favor of scamp is evident. The figures show the number of transmissions versus grid length. At left, grids with 18, 36, 72 vehicles in an area of 1.44 square kilometers, and at right, grids with 50, 100, 200 vehicles in an area of 9 square kilometers. The protocol is identified with GC, Geocast SB, Scamp. The number on the right indicates the number of vehicles on the grid. GC72 indicates that the graph corresponds to Geocast with a grid of 72 vehicles. The figures show the occupancy rate versus grid length. At left, occupancy rate of 36 parking spaces with different grid lengths with 18, 36, 72 vehicles in an area of 1.44 square kilometers, and at right, occupancy rate of 100 parking spaces with different grid lengths with 50, 100, 200 vehicles in an area of 9 square kilometers. The figures show parking search time versus grid length. At left, grids with 18, 36, 72 vehicles in an area of 1.44 square kilometers, and at right, with 50, 100, 200 vehicles in an area of 9 square kilometers. The figures show distance to destination versus grid length. At left, grids with 18, 36, 72 vehicles in an area of 1.44 square kilometers, and at right, grids with 50, 100, 200 vehicles in an area of 9 square kilometers. The figures show successful ratio of finding parking versus grid length. At left, grids with 18, 36, 72 vehicles in an area of 1.44 square kilometers, and at right, grids with 50, 100, 200 vehicles in an area of 9 square kilometers. Let's analyze the per-machine match times under centralized and opportunistic networks. The centralized method, which processes all the demands of a powerful server, is the most common way so far. The opportunistic method allows all vehicles and RSIs to participate in content matching to share maintenance tasks. Therefore, every machine, vehicle or RSI, needs minimal computing power that matches the interests of its neighborhoods and the data it holds. In addition, SCAMP does not respond to the interests of each user, since it calculates what is the most appropriate action to take. When there are too few vehicles, interested parties may have to travel farther to get an acceptable response. With low vehicle density, SCAMP does more pairings than Geocast. When vehicle density increases, Geocast makes more pairings due to higher forwarding and response generated to packets. In an area of 9 square kilometers, the figures show: at left, matching times per machine, and at right, transmitted packets via mobile network. In an area of 9 square kilometers, the figures show: at left, occupancy rate of parking spaces, and at right, successful ratio of finding parking. In an area of 9 square kilometers, the figures show: at left, required time to find a parking place, and at right, distance from parking to destination. Parking meters must not only collect information from sensors on the road, but must also be considered service agents, providing parking information to passing drivers, this through wireless communications. In other words, roadside equipment must increase service availability and offer a promising future to the vehicle network. The figures show a driver's timeline as they travel to a destination. Figure A, driving time without worrying about parking, and Figure B, including the time spent searching for parking with the help of the publish subscribe service. The driver chooses a destination and then heads to it. Upon arrival, the driver must register a parking space and walk to the destination. Travel time is the sum of driving, parking and walking durations. Driving time is related to travel distance and real-time traffic. Parking search time and walking distance are relevant to traffic congestion, occupancy, and turnover rates. Parking competition is often considered as a parking game. The payoff is usually counted from a comprehensive consideration of parking search time, parking fee and walking distance. Most time, the off-street parking has enough capacity to receive those cruising drivers. However, drivers may shy away from higher parking fees and prefer to circle their destinations to wait for a treat, namely a cheap, or free parking spot on the street. The utility function from the viewpoint of driver will be to minimize the total travel cost. The utility function from the viewpoint of the municipality is different. The city only cares if the parking place is used, not who is parking on it. Thus, the utility will be to maximize the revenue and minimize the CO2 emission. The table shows information of the parking game, driver I versus parking place J. Pij is the probability that the driver I chooses the parking place J. It is generally affected by drivers' mental preferences, such as parking fee, walking distance, and the cumulative parking search time. Cj is the fee in the parking place J. C-gas is the extra fuel cost for one vehicle to look for next parking place. To define the parking game, we set drivers as players, parking choices as the set of actions, choose or not choose, and a set of preferences which affect the payoffs. The payoffs of driver I are in blue, and in red, for the otherwise 0-1 drivers. The figure shows the illustration of the publish-subscribe service that supports moving vehicles and roadside infrastructure. 4 agents participate in the service: publisher, subscriber broker, and carrier. The figure shows the dynamic environment of simulation models. Dynamic environment can be simulated by the combination of mobility and radio propagation models. Mobility model is used to describe drivers' mobility. Trace-based vehicular mobility describes the inter-contact times and duration between vehicles. It also provides more realistic probabilities of sending out messages. Synthetic models allow to reproduce drivers' mobility and show the impact from application on waypoints. The radio propagation model is also very important. In reality, wireless communications are very sensitive to the urban terrain, such as buildings, urban objects or vehicles. A realistic geographic restricted path loss model is required to describe the channel properties. Ideally, a combination of real vehicle trace and a geographic-based path loss model will be perfect to evaluate vehicular services. However, path loss calculation shall be modeled from collected data of link quality. It is quite difficult to combine them. Thus, most trace-based mobility models often adopt a free space path loss model which only considers the distance between senders and receivers. In geographic restricted path loss is then possible to implement with synthetic mobility models since the mobility environment is predefined according to the context. The figure shows the mobility models. A. Synthetic with geographically restricted loss of trajectory, and B. Actual trace of the vehicle with road loss in free space. The figure shows an overview of a heterogeneous network. With the popularity of smartphone and connected cars, users often hold a device which supports several different mediums. Now it is very common that if users cannot get enough medium resource from mobile network, they switch right now to Wi-Fi access points, or even to point-to-point Bluetooth communication. Vehicular network adopts the IEEE 802.11p standard and basically uses carrier sense technology to allocate bandwidth dynamically, and benefits from its compatibility with Wi-Fi and can be seen as an offloading alternative. The yellow bricks are for the publish-subscribe service, where SCAMP model is implemented. The pink bricks represent the protocol stack for vehicular networks, and the blue bricks represent the protocol stack for mobile networks. In vehicular network, the corner propagation is considered the mobility model. In mobile networks, Okamura Hata is used. The two environments both apply single channel and have no mutual interference. A smart device shall be able to detect the data rates and prices of different interfaces to evacuate queued packets more rapidly. In an area of 9 square kilometers, using a heterogeneous network, the figures show. At left, the required time to find a parking place, and at right, the distance from origin to destination. In an area of 9 square kilometers, using a heterogeneous network, the figures show. At left, successful ratio of finding parking, %, and at right, occupancy rate of parking spaces, %. There are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until, in the visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied. In the book Human Problem Solving, wrote by Alan Newell and Herbert Simon. Thank you very much for your attention.